the plan for today, for this morning, is so I was asked to talk to you a bit about the research we're doing in Europe. So in my talk, there are two parts. The first part, I'll just talk to you about the European Research Framework Program called H2020 and show you how you can go there and look for and search for safety so that you can look at the calls, the work programs and the projects and the results of these projects in safety. Okay? So I'll show you how to search for that. And in the second part of the talk, I'll talk a bit about what we're doing at CETIC. So CETIC is an applied research center located in Belgium. We're linked to 3 universities and we work with industry, large companies, but also small companies. And I'll talk a bit about the work we're doing in requirements engineering and where we're applying this to safety and security in cyber-physical systems. Okay, so this is the part on the European Research Framework Program. And these are 2 slides that I borrowed with the authorization of the European Commission. So H2020 is the framework program, and it goes from basic research, as you can see on the left of the figure, to market uptake. Okay, initially it was more research oriented, but in these recent years they have tried to close the gap between research and the market. Okay, so and they measure this in terms of time to market. Okay, so basic research is 10-15 years, from any market ready application. Whereas some of there are other programs which are much closer to the market. Okay, so this is important when you're looking for what's happening in Europe, is to be aware at what you're looking at. Is it the basic research or the more applied research? You're interested in what's going to happen, what's going to be on the market in the next 2 to 4 years, or are you looking for longer term research? So bear that in mind when you search. This is the structure of the work program. I won't go into the detail here, but there are 3 big areas. On the bottom there, you see excellence in science. So that's the fundamental research part. Okay, then on the top right, you have this creating industrial leadership and competitive frameworks. This is closer to market, and this is where you have a lot of the applied research. This is the applied research part. And then on the left, you have tackling social challenges. So on the right there, the top right, that's the technical challenges, and on the left, it's the social challenges. So applying the technology to different domains, so for example, transport, health, these different domains that we have. And what you see in green here is the ICT part. Okay, so you won't find there's not one area where you have all of ICT. ICT is a bit spread over into these different parts of the work program. And of course, if you're interested in safety, unfortunately, there's no single place you can go and look to see what's happening in safety. Okay, so safety, large part of it is in the ICT part. You have to go and look for it in the different parts of the work program. So if you're looking for basic research, then you have to go and look for it in the excellence in science. If you're looking for the applied and the technology part, you have to go into the industrial leadership. And if you're interested in the application domains, then you have to look at the societal challenges. Okay. So this is what I want to show you, is how to go and search for what's happening in Europe in terms of safety research. Before I talk, I show you how to search for it. H2020 is collaborative research. So we basically form consortiums of at least, companies, universities, research centers from at least 3 countries in Europe. Okay, but actually this program is open. So other countries that are not in Europe can participate in consortium. And so I just looked up I was wondering, well, can Korea participate in these research projects? And so there's a funding mechanism if you're interested in participating in some of these research projects. It is possible but of course you have to go and find a consortium and get involved into a proposal, and then it has to be funded. It's very competitive. Success rates are only about 5%, 5 to 10%, but it is possible. Okay, so how to find safety-related calls. This is the European Commission, the Research and Innovation website, and in the presentation, in the textual part of the presentation, you have the URL. So if you want to go and search this, you can find the URL there. And so you have to go in funding opportunities, and you can type in a keyword, a search keyword, and I typed in safety. Okay, and this brings up a number of results, and I'll just take one and show you, what it looks like. So I took a call called H2020 ART 2016-2017 that talks about safety in the transport domain. Okay, so this is what I found. So you can go and click on that link, and this will take you to the call page where you have a reference to the work program. Okay, so you can also go and search the work program, and you have a description of this call and where you see that safety is involved in this call. Okay, so it's not a call on safety, it's a call about automated road transport here, but they do take safety into consideration. Okay, so you can go and look at the work program. Okay, so it's a document, and you can search for safety in there, and this will give you information about what are expected from proposals that will be submitted. Okay, so you can search for safety, and you will find how the work program is described. Okay, so this is interesting because in the work program you will find the problems, the description of the research problems that we think need to be solved in the next 2 or 3 years. So it's not always long-term, but it's in the work program. This is for 2016-2017. These are the problems we think that needs to be worked upon in the next 2 years. Okay, so you can go and search and look for information there. Now you can go deeper into the call, and calls are broken down into topics, and this is one topic, just an example to show you what kind of information you can find. And this one is safety and end-user acceptance aspects of road automation in the transition period. So transition period, what they mean about that, it's the period where you will have conventional cars with a driver and automated cars with no driver. Okay, so there's a transition period where you have these two types of vehicles. So this is what this topic is about. Okay, that part was about how to find calls and the work programs. This is more about finding projects, ongoing and past projects, and looking at what projects have been funded and what have they produced as research results. So this is another website, and again the URL is in the presentation. If you look at the textual part of the presentation, you will find the URL, and you can type in keywords that you want to search for in the projects. And here I just typed in assurance and certification of cyber physical systems. Okay, I typed that in, and this will bring up a number of results. Some are projects, some are documents, and I'll just, again, this is one specific example of a project, an ongoing project called AMASS. Okay, so you can click on that, and that will take you to a description of this project. So you see that the title is Architecture-Driven, Multi-Concern and Seamless Assurance and Certification of Cyber Physical Systems. And you will find information such as project details, the objective, who's the coordinator of this project, and who are the participants. Okay, and this is it's an interesting project because they're basically building a platform to gather information, from requirements, architecture, tests. They gather the information to build the safety cases so that people that certify these systems have an easier time than having to interview people. So it's building a process platform to automate some of this work. From here, you can go to the project webpage. Okay, so this is no longer the commission webpage, but the project webpage where you will find more information. And typically, if you can find deliverables. So the deliverables are the project results, and that they're publicly available. So you can download this and see and look at the results of these projects. Okay. This is another example. As my first slide showed, it goes from basic research to the market. Okay, and they have what they call PPPs, so public-private partnerships. So these are basically industry-driven. Okay, and the work program in those are industry defined by industry. Okay, so it's a bit closer to market, and this PPP is called ECSEL, ECSEL, and this one is in the area of electronics. Okay, so and there's a lot of research about safety in there, so you could go in and look there for safety-related research. Another example is Shift to Rail. This is again a PPP in the area of railways. Okay, so, and this is new. These PPPs are rather new. It's the European Commission trying to bridge the gap between more basic research and the market. So they've gotten European industry to collaborate and basically build these work programs to fund research. And again, you can go there, and there's a lot of safety-related research in there. Okay. Okay, now I'm coming to the second part of my talk, which is more the work we're doing at CETIC in this area. And and what do we think are challenges in cyber physical system safety and security? Okay, and so the thing we see is that there's a growing trend to connect these cyber physical systems to the internet. Okay, this makes it easy to manage these systems, but it also exposes them anytime you connect anything to the internet. You're exposing these systems to cyber attacks, and many companies, that we've worked with, they used to work on these safety systems and didn't have much experience in securing these systems. So this is a bit new for at least a number of them that we're working with. So this growing adoption is a bit pervasive in different sectors, automotive, railway, aerospace, space, energy, manufacturing. And these cyber physical systems, at the bottom here you have the typical diagram where you have a physical part on the left, and then interfaces where you have sensors and actuators, and on the right part you have the embedded systems with networks. Okay, so that's your typical cyber physical systems, and they're being deployed more and more in all of these application domains. And this is just one, whoops, there was an animation there, but it doesn't seem to work, but okay. So this one is intelligent transport systems, okay, and automotive in practice. So the background picture shows you different transport, boats, planes, trains, subways, trams, cars, and they're all starting to communicate, between each other. And the bottom part of the figure is just the diagram from the 5G PPP. So this is the networking part, where they show what connecting cars means in terms of communication. So as you can see, it's a complex communication system, linking all these cars. And of course, this exposes, this system to cyber attacks. This is another example in the railways. So this is what they're working on, and they even talk about digital railways. So this is what they're doing in Shift to Rail. They're really talking about data-enabled railway. So they're really looking at railways as connected systems, producing data, pre-trip, during trip, post-trip, okay? And fortunately, they view digital railways as an opportunity to increase safety and cybersecurity. Okay, so part of their work program, the Shift to Rail work program, is about defining standards for European railways to protect the trains and increase security. But they have to agree on standards in Europe. And this is what they're working on. So currently they're doing this. Okay, this is a case study that we worked on in the automotive sector. Okay, so it's the connected car, and as you can see, cars now have many cyber physical systems, and these cars are connected to the internet, and there are many systems. Okay, and you can wonder, okay, are these systems secure enough? So I just searched a bit the internet, and I have two examples here which I found pretty easily. And luckily these were these were things that researchers found. Okay, and so in this case here, it was on a Jeep. The researchers managed to take control of a car, and basically they could control the cold air. They could control the seats. They could control the radio stations. They could turn the windshield wipers on and off. They could take pictures. They could display photos of the hackers themselves on the digital display of the car, and all this remotely from a laptop. Okay, and they could even take control of the steering, the brakes, and the transmission. Okay, so it just shows you that obviously this car was not protected enough, and so there's work to be done. This is another example on a Tesla where researchers again. So these were not really real hackers, but researchers managed to hack into the Tesla car. And they could control the sunroof, the central display, the door locks, and even the braking system. And yet, Tesla is a cybersecurity conscious, car manufacturer, and they even have a bug bounty program, So they're really doing efforts, and even though they have all these efforts to secure their car, hackers were able to hack into the Tesla and take control of the car. Okay. We need to improve the way these systems are designed. Okay, and so this work that's been done on how to link safety and security engineering. And so here there was a European project. This is an ITEA project. Okay, it was called the MERGE project, and they looked into how to merge safety and security engineering. Okay, and they basically said there are different ways to do it. Either you say safety is the most important, and then you take security and you try to integrate security into a safety engineering approach, or you do it the other way. You take a security engineering approach, and then you try to add safety engineering concepts into that. And the third option was to basically co-engineer safety and security. Okay? So at CETIC, we were interested by this last option and this idea of co-engineering safety and security requirements. So if you look at safety and security engineering methodologies, so this is what we did here in this table. So these were methodologies developed in two different communities. So you have the safety engineering community and the security engineering community. Okay, and you can compare them. And so, for example, if you look at goals, both methods have the concept of goal. So in one case, it's called safety goal, and the other one is security goal. If you look at obstacles, so things that break the goals, in safety you talk about hazards, and in security you'll talk about threats. Okay, but it's a bit similar. And you can refine, so you can refine goals and obstacles. And so in safety, you talk about root cause, which is the root cause of a safety hazard. And in security, you can go down to finding vulnerabilities. Okay. If you look at the refinement methods in safety engineering, you'll see you have fault tree analysis, HAZOP, FMECA. In security, you have attack trees, threat trees. Okay. And again, there are different ways to deal with the obstacles. So in safety engineering, you talk about obstacle elimination, obstacle reduction, obstacle tolerance, and goal restoration. In security, you talk about vulnerability removal, isolation, attack recovery, attack impact reduction. Okay. And the standards, of course, are different. So in safety, you have IEC 61508, ISO 26262, DO 178B, etc. And in security, one of the ones we've worked with is common criteria. Okay, so I'd like to talk a bit about requirements engineering. And so this is the area we've been working. So this is really the first phase of the software engineering life cycle. And so what you try to identify there are the services that are required and the constraints under which they operate. And a requirement specification, usually it's a written document in natural language. Okay, and we know that natural language is a bit, it can have, you have problems of ambiguity. So if you read a requirements document, different people can have different interpretations of what's written. And that's inherent to natural language. There's often a bit of confusion between functions, constraints, goals, and design elements may be mixed into the requirements. Okay, so it's not always easy to read a requirements document in natural language. And very often, several requirements are mixed together. Okay, so what we've been working at CETIC is, instead of writing requirements in natural language in a document, we have a model-based approach. Okay, so in software engineering, models have been used. You have lots of models, and for architecture and design, we all know UML models. But UML models basically just describe the solution. You talk about components, databases, things like that. Whereas in requirements, we try to define the problem. Okay, so we're not trying to describe the solution, but we're trying to describe the problem. What's the problem we're trying to solve? And so we build models describing the problem. we speak about requirement specification qualities. And I just want to talk briefly about two of these here, completeness and consistency. And I just want to try to convince you that if you analyze safety and security, separately, which is very often the way it's done, there's no way you can be complete or, be sure that you're consistent. Okay, because completeness means that you have described all services and constraint that should be included in the system. Okay, and a more specific definition, which is the one that we use, is that the requirements and the assumptions, so the assumptions you make on the environment in which the system is supposed to function, and the domain properties have to imply that the objectives of your system. Okay, so this is the way we define completeness of a requirement specification. And consistency, there should be no conflicts or contradictions in the descriptions. And again, that means that if you take the requirements, the assumptions, and the domain properties, you have to write something that's consistent and where there is a solution. Okay. This is just a taxonomy of non-functional requirements, and I just wanted to draw your attention again that again, if you analyze safety and security separately, you're missing a lot. And so in requirements engineering, it's always been natural to try to model the requirements together. Okay, and so safety and security are just two types of non-functional requirements among many others. Okay, this is the language that we use for we call it goal-oriented requirements engineering. Okay, and I won't go into the details of the language. This is the syntax of the language that we use. But what I want to point out is that we answer four fundamental questions when we describe requirements. We try to describe what the system is composed of, so that's the bottom right there, it's the objects of the system. How is it done? So that's the operations, and that describes the state transitions of your system. And then we also identify the agent who's responsible for making these state transitions, and more importantly, why are the agents allowed to make these transitions? Okay. This describes the language. This is the graphical syntax of the language we use. This is the way we integrate safety and security. Okay, so I had an animation, I'm sorry, but apparently the animation's not there, so I'll have to comment the diagram as it is. So on the top left, you have a safety requirement. Okay, so it's this blue box with requirement 1. That's a safety requirement. And then just underneath the hazard is something that can break that requirement. Okay, but again, it's a safety hazard. Okay, and if you go down, so you decompose the hazard, on the left part, you see that there's a root cause, so you've gotten to the basic element that can cause a hazard, okay, and that can break a safety requirement. And then you have a resolution, okay, that can address the root cause. So this is the way you mitigate the risk that you have of breaking a safety requirement. On the right part of the figure, you have a security requirement, and there the language is a bit different. You have an attacker, so this is an agent that can attack a certain requirement, and with an exploit, and he can use he can exploit a vulnerability to gain access to the system and to break a requirement. Okay, and again, there's a resolution, so you can mitigate vulnerabilities, but you have to describe this. Okay, and so you can see here in the language allows to mix security and safety. And so it shows here that the vulnerability, the security vulnerability, can create a hazard to a safety goal. So this is the way we model the interaction between security and safety. Okay, so this is the language, and I have an example. Okay, so again here I had an animation here, but it's not working. But I'll walk you through. So on the right part of the figure, you have automatic braking. So this means that it's a car or a vehicle with an automatic braking system. And we've decomposed this into two goals. Okay? One is called detect automatic braking condition. Okay? So this is a part of the goal that has to detect all the conditions in which you have to automatically brake. Okay? And then the right part, which we've called automatic braking when braking condition, that's the braking part. So when a condition for automatic braking is detected, then the system has to, slow down or stop the car. Okay, so this is a very simple, goal decomposition. And then what we have on the left in red there is it's a negation. So we take the goal detect automatic braking condition and we negate it, and then we call it failure to detect braking condition. Okay. So this is a safety hazard, okay, and we've decomposed this into two cases. You can have a sensor failure, and this can happen, okay. So this is a safety; it's a root cause of a hazard, okay, and the mitigation there is to have redundant sensors. Okay, this is the way you would describe it. And then on the right part, you have a sensor that's been disabled. So this is a security, vulnerability, okay, which can be exploited by a car attacker. But again, if a sensor is disabled, this will create a failure to detect the braking condition. Okay, so you can see here that the security goal impacts the safety goal. And again, here you could mitigate it by having redundant sensors. Okay. So this just shows you, it's an example of how we use the language to model the interaction between safety and security, in cyber-physical systems. Okay, let me see. Okay. I had another slide. This is not the latest version. It's not the latest version of the presentation. I'm sorry, but you'll get that. It will be made available. This is a more complete version of the case study, and the part I described is the part on the lower left. Okay, this is what I described to you. And on the right, on the bottom right part, you have the other part, which is the automatic braking part, where we analyze safety hazards to that goal. And so we again here you see the nice interplay between security and safety, and how to mitigate, the decisions that you're taking to mitigate some of these interactions. Okay, and this was produced, with a tool, and I've put the URL of the tool at the bottom left here, so that you can, if you want to try it, if you want to try modeling a problem with this tool, this is possible. Okay, to conclude, so this growing trend to connect, cyber-physical systems to the internet, and again, this exposes these systems to security, to cyber attacks. So at CETIC, we've very naturally, since we come from the area of, we've been working in the area of requirements engineering, it's very natural for us to model both safety and security together, okay? And we're not safety, we haven't been working exclusively on safety, so for us it's very natural to try to model both, together. And so here I try to illustrate the language that we use, the requirements engineering language, which is a goal-oriented language. So the diagrams I showed you are mostly goals, so explaining why a system has to work and what are the threats, to the behavior, to the correct behavior of the system. So I didn't show you any operations or objects, okay? It was just mostly goals and goal decomposition. So that's the why, answering why. And so future work, we're going to start a project in the next month that will be dealing exactly with this, which is how to update the security functions and data in a safety critical system. And we will try to use this approach, this requirements modeling approach, to see if it helps us in the design of updating safety critical functions. And this will be in the context of trains, okay, not cars. I just took this as a case study. But we're working more in the railway domain. Okay, so that's it for the presentation, and thank you for your attention. And I'll be available after if you have any questions. Okay, thank you.